Hi everyone, my name is Shiloja and here I am going to start with the unit Descriptive Statistics and Probability. The topic Descriptive Statistics and Probability will be dividing this topic into two parts. The first part will be Descriptive Statistics and then we will look into Probability. The main topics that we are going to cover inside Descriptive Statistics are measures of central tendency, measures of dispersion, skewness and kurtosis. So let's look into what are measures of central tendency. Measures of central tendency. When we have a data which is too big and we need to represent its average or some properties of the data, we use measures of central tendency. That is, we calculate a single value which can represent all the properties of the data. The important measures of central tendencies that we are going to discuss here are arithmetic mean, geometric mean, harmonic mean, median, and mode. The first one, arithmetic mean. Let's look into the example, a simple example, and calculate or understand what is arithmetic mean. See, the first example is calculate the arithmetic mean of 12, 18, 14, 15, and 16. There are 5 numbers and we have to calculate the x bar, which is the mean. So it is a raw data. We can see that is 12 is represented one time and each and every values are represented only one times. So we are going to use this definition for raw data, which is x bar is nothing but summation of the all the observations divided by the number of observations. So we are going to add 12 plus 18 plus 14 plus 15 plus 16 and divide it by the total number of observation, which is 5, and the answer is 15. But there will be data where 12 will be repeated some 10 times or 18 will be repeated some 2 times. That is called frequency data. Here x1, x2, etc. xn are n observations and their frequencies are f1, f2, etc. fn. That is, x1 is repeated f1 times, x2 is repeated f2 times, and xn is repeated fn times. To find the arithmetic mean of such problems, we are using this equation. X bar is equal to summation fx divided by capital N. Capital N is nothing but the total frequency. Let's look into some example for that. That is, we'll consider x is equal to 5, 6, and 7. And its frequencies are 3, 8, and 12. So to find the x bar, which is mean, first we have to find f into x. 5 into 3, 15. 6, 8, we will find 48. And 7, 12, we will find 84. And we will add this summation fx and then we will divide it by n, which is nothing but the addition of the all frequencies. Okay, now we have got what is arithmetic mean. Now there is a shortcut method for arithmetic mean. If we consider this example for calculate arithmetic mean of 305, 320, 332 and 350, we can see that these are large numbers. There might be examples of some 1,50,000 etc. numbers coming. So it's very difficult to find the arithmetic mean using the summation of the observations divided by number of observations equation. So here we find out a shortcut method, which equation is x bar is equal to a plus summation d by n. And a is nothing but an assumed mean. We are assuming a mean from the given observations. We select this observation such that it is not too much and it is not too less. Here we can see 320 is somewhat the middle of the equation. 305 is not too lesser than 320 and 350 is not too greater than 320. So we take a as 320 and we find b such that x minus a. X is nothing but the observations. So we subtract this a 320 from each and every observation of x and we find out d, and the total d is 27. And we consider x bar is equal to a plus summation d by n, which is nothing but 320 plus 27 divided by 4. 4 is the total number. This is the shortcut method. Okay. And similarly, there is shortcut method for the frequency data too. We'll just add f frequency into this d. Now we'll look into the properties of arithmetic mean. The first one is AM is preserved under linear transformation of scale. It is simply nothing but if ya equal to a plus b into xi is linear. It is a linear equation. Then if we take the arithmetic mean of the same equation, that is y bar is equal to a plus bx bar, then the equation is linear, same as the ya plus yi equal to a plus bxi. And the second property is the mean of sum of variables is equal to the sum of means of variables. That is, consider x1, x2, etc., xn are the variables. Then mean of the sum of variables, that is, mean we are finding using expectation, x1 plus x2 plus etc. plus xn is equal to sum of means of variables. Mean of x1 will be expectation of x1 plus etc. plus expectation of xn. Okay, let us look into the second property. The mean of sum of variables is equal to the sum of means of variables. Let us consider x1, x2, etc., xn as independent variables. And it is saying that mean of sum of variables, which is expectation of x1 plus etc. plus xn, will be equal to the sum of means of variables. Sum of means of variables is nothing but expectation of x1 plus etc. plus expectation of xn. This is the second property. Now the third property, algebraic sum of deviation of every observation from the arithmetic mean is 0. That is, every observation with it is at xi and its deviation from mean will be x bar. Its sum will be equal to 0. This is the third property. And the fourth property is, if there are n1 observations and its arithmetic mean is x1 and there are n2 observations with arithmetic mean x2 bar, then the combined arithmetic mean of the n1 plus n2 observations will be x bar is equal to n1 into x1 bar plus n2 into x2 bar divided by n1 plus n2. Then the algebraic sum of the squares of the observation from AM is always minimum, which is squares of deviation of observation, which is xi minus x bar square. Its sum will be always minimum. These are the 5 properties of arithmetic mean. Now the next topic is geometric mean. Geometric mean is nothing but finding the appropriate root or the nth root of variables. If there are x1, x2, etc., xn, n variables, then its geometric mean will be nothing but nth root of x1 into x2, x2 into etc. into xn. And using the logarithmic formula, we can change it into this format, which is anti-log of summation log x divided by n. And if this is for an odd data, and if there are frequency data, that is x1 is repeated f1 times, etc., xn is repeated fn times, then we will find the nth root, n will be capital. It is the total number of frequencies. Nth root of x1 power f1 into x2 power f2, etc. into xn power fn. And same as the raw data equation, we can convert it into logarithmic equation, anti-log of summation f into log s divided by capital N. N is nothing but the summation of frequencies. Okay. And the third topic is harmonic mean. Harmonic mean is known as the reciprocal of arithmetic mean. Let's see why. Arithmetic mean, we have x bar is equal to 1 summation x divided by small n. N is the total number of variables and x are the variables. Here we can see the harmonic mean equation is nothing but n divided by summation 1 by x. That is, if we have a data x, we have to find 1 by x and its summation 1 by x and then divide n by that number. Summation 1 by x, whichever we are getting, will divide. Okay, the harmonic mean equation for the raw data is nothing but n divided by summation 1 by x, which is the reciprocal of the arithmetic mean we have found out in the previous slide. Then for frequency data, if frequency is there, we will multiply f into 1 by x. For arithmetic mean, we multiplied f into x. This is for arithmetic mean. And for harmonic mean, we find out f into 1 by x, and we will find out the summation of f by x and then calculate the harmonic mean for the frequency data. The fourth topic under measures of central tendency is median. As the word suggests, it is the mid value, that is, the middlemost value of a data when it is arranged in ascending or descending order is the median value. If there are odd number of observations, for odd number of observations, the middle value will be the median. See, if there are 1, 2, 3, the middle value is 2. Simply we can say it is 2. But consider if there are 4 values and 4. Can we find out which is the middlemost value from these 2 are there and here 2 are there. There is no middle value. So we have to find out it using this one. The average of n by 2 and n by 2 plus 1 observation. That is, if there are even numbers of observation, the median will be the average of n by 2 and n by 2 plus 1 observation. So here n by 2, here for n equal to 4, there are 4 observations. So n by 2 will be 2 and n by 2 plus 1 will be 3. So we are going to find the average of this, that is 2 plus 3 divided by 2, which is 5 by 2 equal to 2.5 is the median of this data. Okay, when there are even number of observations, we find out the which is the n by 2th observation and n by 2 plus 1th observation and find the average of it. Next, finding the median for a frequency data, we'll use this equation, which is nothing, but I'll explain each and everything. N we have already know, n is equal to summation of f. M is the cumulative frequency up to the median class. We will consider a median class which is in which the half of the data falls. Then we will find and we will add another column of cumulative frequency and we will find it up to the median class, and that value will be M, and C will be class interval of the median class, and the F will be the frequency of median class. So using these values we can find out the median for a frequency data. The fifth topic under measures of central tendencies will be mode. Mode is that value of the variable which occur maximum number of times in a set of observations. Let us consider a set of observation 5, 8, 10, 5, 2, 3. From this, the maximum number of times which observation is occurring. That is, 5 is occurred 2 times, 8 1 times, 10 1 times, 2 1 times, and 3 1 times. So clearly 5 will be the mode of this observation. In a frequency distribution, mode is defined as the value of variable having the maximum frequency. Suppose for this equal to x and the frequency of this will be 2, 3, 4, 5, 6, 7 I have said calculated. Then the x value which is having maximum number of frequencies will be the mode. And for a continuous frequency distribution, this equation can be used. Z is equal to L plus delta 1 divided by delta 1 plus delta 2 into C. L is the lower limit of model class. In the previous slide, we have calculated the median class and given the values to the equations. Here we are calculating the model class, and L is the lower limit of the model class. C will be the class interval. Delta 1 will be the difference between frequency of model class and the pre-model class. Okay, subtracting the model class and the pre-model class, and delta 2 will be the difference of frequency of the model class and the post-model class. Using that, we can find out the mode for the continuous frequency distribution. Next are the few relationship between the 5 measures of central tendencies that we have discussed. For a moderately asymmetrical distribution, empirical relation is. What is moderately asymmetrical distribution? We know that we consider the standard normal distribution as the asymmetrical distribution. Its graph is like this. So here comes the mean. Whichever graph's shape is not, that is, here most of the data values are concentrated towards the circle. When the data values are distributed as asymmetrically, it is called as asymmetrical distribution. For a moderately asymmetrical distribution, mean minus mode is equal to 3 into mean minus median. This is the equation which can be there for example. Very important equation. Mean minus mode is equal to 3 into mean minus median. This is an empirical relation for an asymmetrical distribution. And for a symmetrical distribution, mean equal to median equal to mode. That is, this is a symmetrical distribution. Here mean equal to median equal to mode. Then for an asymmetrical distribution, again, mean less than median less than mode for a negatively skewed and It will be opposite for a positively skewed. What are negatively skewed and positively skewed distributions? Let us consider this graph and this graph. Okay, here we can say that this is positively skewed and this is negatively skewed. What is skewness we will be discussing detail in the coming slides. So for as of now, negatively skewed will be having mean less than, median less than mode. For a negatively skewed distribution, mode will be greater. Okay, and if there are only two observations, consider A and B are two observations, then GM square is equal to AM into harmonic mean. The product of arithmetic mean and harmonic mean will be the square of the geometric mean. That is a relationship when there are only two observations. So moving to the next topic, which is measures of dispersion. It quantifies the spread or variability in a set of data points. That is, how much variability there is for the data points from the measure of central tendency. Suppose we have calculated a mean and how far or how near the other data points are there from the mean. If it provides the information about how much individual data points differ from the measures of central tendency, whatever we have used, whether it is mean or median or mode, it doesn't matter. And it also helps to suppose this value is x bar we have find out, and here points are there, x1, x2, etc. If and we are calculating the spread or degree of spread or variability among these points, and if the measures of dispersion are too high, means we cannot rely on the measures of central tendency. So for measuring this, there are four methods we have found out: range, quartile deviation, mean deviation, and standard deviation. Let us look into that. The first one is range. Range is the difference between largest and the smallest of given values. From the image only we can understand this is the smallest value and this is the largest value. So here range is found out as 200 by 150 centimeter. We are finding the height of the range of the heights. So 200 by 150 centimeter, 50 centimeter is the range of these 5 people. So here we can see range equal to L minus S. L is the largest value, S is the smallest value. Suppose there are a student scored 100 marks in statistics exam and the lowest ones who scored was 20 marks, then the range is equal to 100 minus 20, which is nothing but 80. And to measure the relativeness of this, we introduce coefficient of range, and the equation is L minus S plus L minus S divided by L plus S, that is coefficient of range. Next, then let us look into the next value, quartile deviation. Quartile is the half of difference between the first and third quartiles. First, we can see what are quartiles. See, there are if this is a data point, we can in quartile we are dividing the quartile into 4 equal parts using 3 data points, which is Q1, Q2, and Q3. See, there are 4 equal parts. These are called quartiles. There will be 4 quartiles. Okay. Similarly, we have percentiles and deciles. In percentiles, deciles we are dividing this one into 10 equal parts using 9 points, and in deciles percentiles we will be dividing this one into P1 etc. P99. That is, percentile will be 100 pieces and deciles will be, we are dividing that into 10, and quartiles we are dividing into 4. So quartile deviation we are finding Q3 minus Q1 by 2. Q3 minus Q1 we can say it as interquartile range. Okay, we are finding the range, the highest value minus the lowest value is range, and the half of the interquartile range is quartile deviation. And similarly, we have here coefficient of quartile deviation. The equation is Q3 minus Q1 divided by Q3 plus Q1. And the third one is mean deviation. Mean deviation, as I have discussed earlier, it is the absolute value of deviation of observation from origin, say mean, median, or mode. There are mean deviation about mean and mean deviation about median. We can see from the equation only, this is the deviation of observation from its mean, and we are finding the absolute value. The sign of doesn't matter if the measure is negative or positive, it doesn't matter. We are finding the absolute value and adding it and dividing by total number of values. That is absolute values of deviation of observation from the origin, from mean. Okay. And here in median, we are considering its variables deviation from its median and dividing by total number of observations. And coefficient of mean deviation about mean is mean deviation about mean divided by mean. And similarly, for median, it will be mean deviation about median divided by median. These are very simple topics. We have to see just simple observation examples and study the equations. The fourth one is standard deviation. Standard deviation is defined as the square root of the arithmetic mean of squares of deviation of observations from A. That is, we are finding the deviation first, xi minus x bar, then squaring, and then finding the sum, adding that, then dividing by the whole number of observation and finding the square root. Finding the square root of arithmetic mean, we are finding summation something divided by n, that is arithmetic mean of square of deviations. Finding the squares of deviation and finding the arithmetic mean and then the square root. Coefficient of standard deviation will be nothing but standard deviation divided by x bar, which is the arithmetic mean, and coefficient of variation is standard deviation divided by arithmetic mean into 100. So these are the measures of dispersion. We have first discussed about measures of central tendencies, then measures of dispersion, and now we are moving into two simple topics, skewness and kurtosis. First, let us look into what is skewness. Skewness is a statistical measure that describes the asymmetry of a probability distribution. As I have discussed previously in the slides of measures of central tendency, I have said that there are symmetric distribution and asymmetric distribution. So these can be understood easily using skewness. From the figure given here, this is a positively skewed. Okay, this one is positively skewed distribution. It is asymmetric distribution and it is positively skewed. That is, more data points on the positive skewness is nothing but the right tail of the distribution is longer. See, this is called as tail. Tail is longer, indicating that there are more data points on the left side of the distribution. See, more data points on the left side, hence mode is on this left side. More data points on the left side, so that is the positively skewed one. Next we can see negative skewness. Here, negative skewness. The left tail of the distribution is longer. Left tail, towards left it will be longer. This is the negative skewness. Left tail it's longer, indicating that more data points lies on the right side. Hence the mode of the negatively skewed distribution will be on the right side. And here we can see the symmetric distribution, which will have mode here, mean here, and median on the same point. That is called as symmetric distribution. We have seen positive skewness, negative skewness, and zero skewness. Zero skewness is nothing but symmetric distribution. It will be the mirror image. The left side and right side of the zero skewed graph will be a mirror image. Now, how to find out skewness? The equation to find out skewness is S is equal to mu3 by sigma power q. Mu3 is nothing but the third moment about mean. Moment we'll be looking into the details of in the upcoming slides, and sigma is the standard deviation. We have seen the equation to find out the standard deviation. Using this equation we find out this is equal to sigma, and then cube of the sigma is taken, cube of the standard deviation is taken, and after finding the moment we can see mu3, and according to the mu3 whether it is positive or negative or zero, we can see whether it is positively skewed, negatively skewed, or zero skewness. And the next topic similarly is kurtosis, which is a statistical measure that describes the shape of the probability distribution. Shape. It describes the shape of the probability distribution. Here previously in skewness it is the symmetry or asymmetry of a distribution, and here we can see it is the shape of a probability distribution. Similar to skewness, kurtosis is also three types, which is leptokurtic, mesokurtic, and platykurtic. Let's look into the mesokurtic one, which is the ideal one. Okay, a distribution with kurtosis equal to 0. It has tails that are similar in shape to normal distribution. I have mentioned that we consider normal distribution as an ideal symmetric distribution. Okay, symmetric distribution. So a normal distribution is mesokurtic. It is having kurtosis value equal to 0. Then leptokurtic will be having, we will see what is leptokurtic, a distribution with heavier tails and a sharper peak than the normal distribution. It indicates more extreme values in the distribution. See, kurtosis is used to find the shape of the distribution. We can see that if we draw a symbol graph, we draw a line graph. There are data points here, but there might be point which lies too much far from the this line graph. That is called as outlier. So if there are more outliers or extreme values in the graph, we can understand that using kurtosis. So if there are more extreme values, it is called leptokurtic. It will be having a heavier tail and a sharper peak. The peak is too sharper. Similarly, if there are less extreme values, the distribution will have lighter tails and a flatter peak. It is called platykurtic. See, the main difference between leptokurtic and platykurtic we can see from the peak. We can understand it from the peak. When the peak is too narrower or flatter, we say it is platykurtic, and the peak is too when the peak is too sharper, we say it has leptokurtic. Now, similar to skewness, there is an equation to find out what is kurtosis. The value of kurtosis, mu for k is equal to mu 4 by sigma 4 minus 3 is the equation to find out kurtosis. Mu 4 is nothing but the fourth moment about mean. For skewness, it was the third moment about mean. For kurtosis, it is the fourth moment about mean, and the fourth power of the standard deviation. See, skewness was mu 3 by sigma power 3, and kurtosis is mu 4 by sigma power 4. Okay, and if the kurtosis values, according to the kurtosis values, we can see whether it is leptokurtic, mesokurtic, or platykurtic. Okay, thank you.